All right, good evening, everyone, and a very warm welcome to the second inaugural lecture of this week. I think it says a lot for Keele that actually we've managed to get such a big audience to 2 nights running, and I recognise quite a few faces that were here last night as well, so congratulations to all of you in particular. It is a pleasure this evening to introduce Mike Watkinson's inaugural lecture. We clearly have 2 types of inaugural lecture in many respects at Keele. We both celebrate the internal promotions that we have, but also, unlike other universities, certainly unlike my previous universities, we also allow our sort of professorial recruits to present their scientific background and their expertise, and I think that greatly enriches what we can do in this lecture series. So as I say, it's a great pleasure to welcome you all here, in particular family members, which does make the lecture that bit more difficult, I have to say, for the new professor in terms of pitching the lecture for a particular audience, but I'm sure Mike will do a great job this evening. So Mike started his career at St Andrews, getting a first in chemistry from there, and then he went on to do his PhD in Manchester I'm a biologist, I don't do chemistry. Inorganic chemistry. From then, he went to the university in Santiago to Compostela, which is in Spain, and he went there as a Royal Society European postdoctoral exchange fellow. He then went back to Manchester, where he did postdoc and started to get his fingers in the pie of lecturing, I think, at that stage as well. And then he moved to Queen Mary University of London, which, when he went there, was Queen Mary and Westfield College, and then he was made Professor of Synthetic Chemistry there in 2010. He had a number of different roles at Queen Mary. We've often exchanged stories about his time on the University Council at that stage, but he was also Doctoral College Director and Deputy Dean for research, in particular around PGRs. He was appointed, importantly, in terms of external profile, because I think that's one of the key things that we look for in our professors, as Chair of the Royal Society of Chemistry Microcyclic and Supramolecule Interest Group in 2016, and then he moved here to Keele just last year to become head of our School of Chemical and Physical Sciences. Mike's general work area is in the design and synthesis of small molecule systems, and in particular for application in sensing and catalysis. So I'm sure that's what we're going to hear about this evening, so it's my great pleasure to ask Mike to deliver his inaugural lecture, Make Me a Molecule, the Power of Synthesis. Thank you.
So, as Trevor alluded to, this is actually my second inaugural lecture, and I've been reflecting on what I did in 2012, and part of me thought, well, shall I just tweak it a little bit? And actually then went and looked at the slides, and the slides were so dated and so old. This is a completely new set. So for Debs and Gemma, who were there, the only people who were there, it is completely new. So Make Me a Molecule, the Power of Synthesis, what I want to do is take you on a journey, really, which, for me, tries to articulate why chemistry is so important, why chemistry is that central science that the RSC keep banging on about, and maybe make a plea to some of those in the audience who maybe think chemistry isn't that important to think again. And we heard last night from Raphael the importance of the periodic table in chemistry, and we're going to go over that ground again, I'm afraid. So the first slide is the one that I was least nervous about until the meeting with Raphael yesterday morning. It's about 10:30. And it was the slide that I was most nervous about when I gave this talk at Queen Mary, because I had completely forgotten that this lecture is recorded and published on YouTube. And so, my dear collaborators, if I've forgotten you, I'm sorry. But I'd just like to thank, particularly on this slide, 2 PhD students, Jessica Pancholi, who is now a postdoc in Oxford, Li Fang, who still works with me at Queen Mary, but is now supervised formally by Chris Jones and Rachel, and an absolutely amazing postdoc who got the research started that I'm going to talk about today, which is Emiliano Tomanini, who now works for Aztecs. I've also been blessed over the years of having some wonderful collaborators, and I particularly highlight Steffi Krause at Queen Mary in the School of Engineering and Material Science, who is the most amazing person to work with. And without her and her brilliant group, some of whom I still co-supervise and we have grants together, help us do what we do. I've been lucky to work with quite a few people externally, including Guy and David. David's now at Birmingham. Steve Goldup was a colleague at Queen Mary. Matt Todd's now actually back at UCL, but was at Sydney for many years and got us working with these people at the university. And of course, all of the funders over the years, and I particularly highlight the Chinese Scholarship Council, who've been tremendous in their support for the work I'm going to talk about tonight. So, I think we have now firmly established in the school that Epping Forest is a big forest. Now, why include this slide? Well, those of you who know me know that we live in northeast London. We actually live more or less on the junction of the M11 and the North Circular. And if we roll out of bed in the morning, Epping Forest is on our doorstep. And so this is the Epping Forest South. And so my normal dog walk in the morning with my little furry friend, who has the worst posture of any dog in the world, is sort of around here and back, and that's about a 40-minute walk. If I take Gemma to school, which I now do on a Friday, then we walk this way down here, it's gone again, down here and round and back, and that's getting on for an hour. And this is my thinking time. And on Friday, after I dropped Gemma off at school, I started thinking about what I was going to say today. And this is time that I've still got here, because of course the walking from Silverdale isn't quite that long, but still that free time to have a think about what the day holds. And what I thought I'd do is actually, having talked to a few people about inaugurals at Keele, sort of reflect a little bit on why I do what I do. And I started thinking, well, why do I do what I do? And I think I can blame my mother for what I do, which this is one of my first memories of the kitchen with Mum, was actually doing paper chromatography on felt tip pens. And then I used to cook a lot, and still do, although the range of things I can cook in Silverdale is somewhat more limited than it is in London. And sadly, I've just been told that the local co-op is shutting for 2 weeks. So I'm either going to get very thin, which I probably need to at the moment, or be calling on my colleagues to take me to larger supermarkets, because, as you all know, online and technology are not my things. The other thing that I remember vividly from my childhood was making a copper sulfate crystal with my dad, and then getting quite into minerals and fossils, and spending time actually with Jem on a beach in Dorset a few years ago, desperately trying to find an iron pyrites ammonite. That then led me to wanting to know why these were coloured, and we had a family friend, who was also a lecturer in inorganic chemistry at Liverpool, David Nichols, who used to do a lot of work at the school I went to, because his children went there too. And that brings me to what the greatest inspiration for, I think, everyone who studies chemistry is, which is always their teacher. And the teachers are so important. And I was blessed at school with having a brilliant chemistry teacher, Jack Kent. But I was also blessed at university of having 3 inspirational people that taught me chemistry and I worked with. The first is obviously not a person, and this is actually the Bob Hay Cup, which is awarded by the macrocyclic supermolecular interest group of the Royal Society of Chemistry that Trevor alluded to, which is bequeathed to the interest group and is actually the only prize, I think, that actually costs the winner money to get, because you have to pay for the cup to be engraved for the next year's winner. And sadly, I couldn't find a picture of Bob online, but Bob taught me bioinorganic chemistry in my 3rd year of my degree, and was a huge inspiration. He used to have a picture of a crystal structure of liver alcohol dehydrogenase on his door. He'd walk through the door and there'd just be clouds of cigarette smoke in his office, and he'd just sort of take the fag out of his mouth and go, "Hi." He was so cool. The other person that was hugely inspirational to me was the middle picture here, which I really can't get this to work, which is David Cole-Hamilton. And David, I did my final year project with at St Andrews. And I got really lucky, because David at the time had the most brilliant postdoc, who's now an academic at Sheffield, below him, called Ahmed Iraqi. And Ahmed was coming towards the end of a 3-year postdoc position. And as a result of that, I hit the ground completely running and got 2 papers out of my project. And from that, I thought, well, this research is really easy, isn't it? Yeah, I think that's what I'm going to do. And from there, we went on. And then the final person that I just want to acknowledge, who was a huge influence on me, is this person, who is Jim Utley, who was the head of department at Queen Mary when I was appointed. And Jim sadly died 2 weeks ago, but I'll be forever grateful to him for giving me, and not the 11 other people that they interviewed for 2 posts, the chance, because Jim put a huge amount of faith in me, and I'll be forever grateful to him for that. So, chemistry, we have some challenges, and I'm just going to go through a few of them. And the first one is something which, sorry, let's go back. The first one is something that one member of the audience is currently experiencing, which is the OCR A-level curriculum, which isn't very interesting, and is also incredibly prescriptive. So as an example, it appears that nylon is still the most interesting polymer as it was when I studied A-level chemistry over 30 years ago. The world has moved on. And we have the problem that people find chemistry hard, and so in organic chemistry, we learn to draw hexagons, and we learn to draw them very well. And then as you get older, you get much worse at drawing hexagons, until they sort of look like squashed things, if anyone has a lecture with me. But what we can do, so those are challenges, to get people to want to study the subject. But what we can do is make jokes that we understand, and we can have little chortles about, that some people look at and go, And some of them are nice, and some of them are universal. So yeah, don't trust atoms, they make up everything. Yeah, okay, you get that. This one is very familiar to some of the ladies in the audience, on the back of a hoodie in the department. And then this one, which is actually not a reaction at all. This is the sort of thing that we do actually get in exam papers, the impossible rearrangement of bonds. But what I mentioned to one of my colleagues yesterday was actually a student at Queen Mary came in with a sweatshirt with the bottom one on. And the reason that this is funny to chemists and no one else in the audience gets it is because this is the Cope rearrangement. So, chemistry has advantages, but chemistry has this massive, massive, massive image problem. If you Google chemical free, it is staggering what marketing materials are out there. So where do you begin as a chemist with this? So first of all, I think the point is that chemical free only benefits pets and children. So if you're grown up, it's okay. But we can have a chemical free home. We can have all natural chemical free cleaners. I'm not sure which of the bottom ones is my favourite. I think the perfume that's chemical free is probably my favourite, but this is just absolute nonsense. So, and again, I was listening to the news earlier in the week. Chemical is a negative word. And we do have an image problem as well, because as you'll see, some of you later, we associate chemistry with men of a certain age, generally with beards, often very thick glasses, and bald heads. We also associate chemistry, the word chemistry, with people who are a bit deranged. And some real professors of chemistry actually do look like the wonderful Martin Polyakov from Nottingham. Bears a striking similarity, I believe, where I'm currently external examiner, so I better be careful. If you try and find images of women doing chemistry, they're always very earnest and generally looking at blue liquids and not wearing safety specs. But you can find earnest men looking at liquids as well. And as one member of the executive commented to me a while ago, you're a chemist, you won't say much, and then made derogatory remarks about my diet and pie and 2 veg. But let's just get that right now for everyone in the audience. Okay. The other thing we have in chemistry is a very serious problem with what's generally now known as the leaky pipeline. The fact that we start off with a relatively balanced undergraduate population, and as we move through the years from PhD to academic to professor, we have this massive drop-off of female colleagues remaining. Chemistry realised this, and it was a guy called Sean McWhinney at the RSC who started looking at data, and the Royal Society of Chemistry actually think have been leaders in this field. I don't think we have got where we need to get just yet, but we're certainly further down the road than we were. And I'd like to acknowledge 4 of my close personal friends who've been shown huge leadership. Polly Arnold, who's at Edinburgh, Leslie Yellowlees, who was president of the RSC, also at Edinburgh, Paul Walton, bottom left, who's at York, who was the first department in the country to get a gold Athena Swan Award, and Dave Smith, who, if you haven't followed him on Twitter yet, Trevor, please do, who champions LGBT rights and also has an adopted child, and it's very vocal. But it's an image problem. And if you now Google chemistry and professor, the world is looking a little bit more diverse. And actually, you do get women, and you do get people who aren't white and male, but we've still got the glasses and the molecule. So do we need more of these? Do we need to change how we present the subject publicly? And that's our job as chemists. But one thing I'm particularly pleased that we've managed to do already in the school, although I can take very little credit for it, is our recent Bronze Athena Swan Award. And I thank everyone who was involved in that, especially Martin Hollenby and Tess Phillips. So as we heard last night from Raphael, this is the 150th anniversary of the periodic table. And those of you of a certain age will remember a few years ago a BT advert of who do you want to have a one-to-one with. And my one-to-one was always Mendeleev, because I was always amazed at the vision and ability to realise that there were elements that hadn't been discovered yet, but that might be. And a lot of my career has been involved in manganese chemistry, and Mendeleev predicted the existence of eka-manganese, which is technetium and used now in radiomedicine. So this is the periodic table that we now have, slightly more complicated than the one we saw last night, which is the kind of naturally occurring elements. This is now, we have all the very heavy elements that are across the bottom that don't quiz me on them because I can't remember them. And our chemistry is associated really with the top half of this periodic table. Mainly the D block, first row, the D block, and the organic elements on the right-hand side. So those are our building blocks for our molecules. But Kiel has a reputation for sustainability, and sustainability is important. And this year, in addition to the normal periodic table, we now have the sustainable periodic table, where we have elements in green which are plentiful, elements that are limited in availability, which are yellow, rising threat from increased use, or it could be that they're mined in single countries like China or South Africa, where we are at risk that we can't get them, or serious threat in the next 100 years. And if you reach into your pocket, I guess you all have one of these. And just to give you an idea of how much chemistry is involved in one of these, there are over 30 chemical elements in them, and some of those are on that endangered list. And in Europe alone, 10 million mobile phones are replaced every month. So this is a major potential problem. And that's just the phone. Think about your TV. Think about all those things around your house. These are things that chemistry impacts on, which leads me on to global challenges and opportunities for chemistry. Clean air, clean water, clean land, clean oceans, sustainable farming, sustainable energy supplies. The one that terrifies me is antibiotic resistance. The aging population and our health. Every single one of these things, chemistry will either give a solution or will contribute to a solution. There has never been a more exciting time to be a chemist than there is now. Which brings me on to some research. And it starts off with a philosophy. And this is a slide that I've used many times in talks. And it comes from a great textbook, which I used to use for undergraduate lectures, which tells us that these boundaries that we put down in chemistry, I'm an inorganic chemist, I'm an organic chemist, I'm a physical chemist, I'm an analytical chemist, they have no meaning to nature. Nature's key is survival. And in the modern world of academia, that applies too. And survival equates to publications and grants. And to be successful and competitive, that's what I think we need to do. And those are my functional benefits of having the grants. So this is where I sort of reflected on Friday while I was walking home about what I wanted to talk about. There's a lot we can talk about. And it's actually moved on a huge amount since the early days that I spoke, or the 2012 days that I spoke about. I hate this. So, up at the top, we have some of my very early research work, where we were trying to develop low-temperature bleaching catalysts for applications in washing powders. These were molecules that would help activate the bleaches that go into washing powders, principally hydrogen peroxide in solid form, which would then clean clothes at lower temperature. And we had some modest success. And at the time, I used to obsess about the cost of heating water up in a washing machine, which is astronomical because of the heat capacity of water, the cost of electricity generation in the developed world. And then one day, I went on an EPSRC sandpit and was told by Procter & Gamble not to worry about that because that was actually trivial. And what was more important was the 7 billion people around the world who spend their entire lives washing clothes. And that if we could emancipate them and allow them to do something else, what a different world we'd have. And so we've worked on and off with that for many years, and we have actually published relatively recently on that, but I'm not going to talk about that today. Nor am I going to talk about the work that we've done over the many years now with Steffi Krause that I alluded to. Here, what we've done is taken a series of essentially cross-linked polymers. So we link a polymer with a short peptide chain, which has a cleavage site which is designed to be cleaved by a specific enzyme. And this started off, which will come as a great amusement to everyone who knows my love of the dentist, with a dental application where we were trying to actually develop technology for the detection of active periodontal disease. And this is actually on the slide here. So this is where we're adding an enzyme called human neutrophil elastase, which our collaborators at the dental school in Sheffield had identified as a marker for active periodontitis. So when you go to the dentist, which I hadn't done for how long was it? 6 years. 6 years, which resulted in a root canal, a crown, a very large bill, and much amusement at home when I had to be sedated, and there's a special bay there for me. You go to the dentist, and they go 1, 2, 0 as they go around your teeth. When they're measuring the depth of the pocket, it's called the pocket, the gap between your gum and your tooth. And within that, there's something called cervicular gingival fluid. And in that fluid, there are 4 enzymes that we identified as markers and developed sensor technology to detect. And that was actually an impact case study in the last ref. We've moved on from there, though, quite considerably. And we now are working much more on modification of surfaces, now trying to link the surface modification to actually some of the functional complexes. And we've just got an EPCERT grant that started not long after I started here, where we've got a postdoc in London, and we'll have some manpower up here to work on that. But what I'm going to talk to you about today is the bottom part, which is the ligand design for functional complexes, where we're looking to make a molecule that has a very, very specific purpose. And in this case, what we're looking to do is image zinc. And so the rest of the talk is going to focus entirely on imaging mobile zinc. So for those of you in the audience who aren't chemists, this is the explanation slide. There'll be one for the chemists in a little while. It's a little bit more high-tech, but not too bad. Essentially, what we're developing is we're trying to make a molecule which has some sort of receptor for an analyte. And in this case, our analyte is zinc. It's going to be linked by a short spacer to a signaling unit. And in our case, the signaling unit fluoresces. It switches on and emits light when the zinc binds, which I'm trying to represent here. And those of you who know me, I did promise that there were going to be no football jokes, but you'll be not surprised to learn that we focused a lot of our work on a blue-emitting sensor device. And here's just a really nice example from the literature that actually isn't terribly useful because it only works in organic solvents. But it's a really beautiful example where as you increase the concentration of zinc, the zinc binds first of all to a weak binding unit, then moves to a slightly stronger binding unit, and then ring opens this spirolactam, which then gives the range of colours. So it's a really beautiful piece of chemistry. But then there's some undergraduates here, and they're probably sitting there thinking, zinc, zinc, zinc. I don't know anything about zinc because we don't really teach very much zinc chemistry. The reason that we don't teach very much zinc chemistry is to chemists it's really boring. It doesn't do anything. It's a little round sphere of charge. It's hard to detect for that reason, so we can't do any real useful spectroscopic tools that we like. It doesn't interest us, but nature uses it. It's hugely important. Really boring. I can't emphasize enough how boring it is. But it's incredibly useful. And what I'm going to do now is ask you all just to do a little karate warm-up exercise that we do in the Silverdale area. Be careful of the people around you, but I just want you to put your arms out and start crunching your fingers. Sensei Josh, do you want to take over? Or can I do this one? So we do that. Normally we go that now, but I think there might be some carnage. Turn them over, turn them back, and now squeeze. And start again. And we do this for a little while, and it starts to hurt quite a lot about here. But have any of you wondered why your fingers didn't just explode? Because they should have done, shouldn't they? Because what you're all doing is you're burning carbohydrate to use the energy and generating carbon dioxide. Carbon dioxide is a gas. Blood is a liquid, which it doesn't dissolve in terribly well. But my hand's not exploding. Why? And it's because of zinc. So there's an enzyme called carbonic anhydrase, which is converting that CO2 gas at a diffusionally controlled rate. So it's happening as fast as the molecule can diffuse into the enzyme and out of the enzyme, and it's taking it to your lungs, through your blood, and you breathe it out. Those of you who had a glass of wine before the lecture, you're currently using zinc as a structural factor in liver alcohol dehydrogenase. And the reason alcohol's bad for you is not because of that enzyme, it's because of the next enzyme up the stream, which is really rubbish, which is aldehyde oxidase, which is a molybdenum-based enzyme, and I can't say anything good about the lower part of the D block elements. So zinc's really important in enzymes. We're not interested in those, but it's estimated to be about 10% of our genome is made up of zinc enzymes. So they do a huge amount of stuff, but we're not interested in that. What we are interested in is zinc transportation, which is really, really, really complicated. So again, if I said, tell me a trace element in you, you'd all have gone for iron. Iron's modestly complicated with 7 transporters. Copper's important biologically, only 4. Zinc's got 24. That's a lot of biology to go wrong. And because that's a lot of biology to go wrong, zinc is associated with many, many disease states. And this just shows you where these various zinc transporters are in the cell. I feel obliged to include some cell imagery in this talk to please the Vice-Chancellor and the Dean for the faculty. And please don't ask me any questions about cell biology. So we have 2 areas that we're just going to focus on. 2 areas we're going to focus on today. One is ZIP7, which we think is linked with breast cancer. And one is ZNT8, which there is a link with type 2 diabetes mellitus. But lots of other stuff going on there. So possible question is, should we take supplementary zinc in our diets? Well, if you eat a balanced diet, you probably should do, but you may be aware that a few years ago there was talk that zinc was a cure for the common cold, and I do actually take a zinc and vitamin C supplement, and up until Christmas I hadn't had a cold for as many years as I could remember, but I think that's a very limited study. But if we look at our zinc we're interested in this pool of what's called free zinc or mobile zinc. And this ranges from the femtomolar in concentration right the way through to the millimolar. So in the back of your eye, there's a thing called the Brooks membrane, which is where peptide plaques form when you get age-related macular degeneration. And guess what? Zinc's associated with that. When you get plaques in your brain, zinc's associated with that. It's intimately involved in your central nervous system. In the males in the audience, if you suffer from prostate cancer, we know that zinc levels will fall through the floor. And if you're a female in the audience, that if you suffer from breast cancer, that zinc levels are elevated. What we don't know is whether that's causal or symptomatic. And so part of this research is focused on trying to help biomedical scientists, biologists, have better tools to do better experiments. And if my dear friend Nikki Lowe, who's actually here, she's a Global Challenges Research Fund ambassador who was here at Keele a little while ago, were here. She's actually a dietary scientist, and she would say, yeah, and they all get knocked on the head completely in the third world by infantile diarrhea, which is also associated with zinc. So going back to this, how do these things switch on? This is our standard, what's called a photon-induced electron transfer mechanism. So we have some sort of fluorophore. In our case, it's the naphthalamide I'll show you in a moment, but in this case, it's just a simple Bo-Dippy system, which we can excite with light. And if there's a pair of electrons nearby, which are of the right energy, which are normally associated with the nitrogen, here's our little linker. For those of you who aren't chemists, that's just a carbon atom, our little linker. These electrons can hop in here and quench fluorescence. So fluorescence is switched off. However, if we bind our zinc, what happens is that these electrons become lower in energy because they're now involved in a bonding interaction, and it becomes impossible for them to hop across and quench that fluorescence, and fluorescence is switched on. So, I need to now do a second demonstration. So we use click chemistry. So again, for the chemists in the audience, you are familiar with click chemistry. You know what it is. For those who aren't, it's very simple. It was a term that was created, or it's a concept that was created by Barry Sharpless, who won the Nobel Prize for Chemistry in 2001, in which he said that any reaction that was modular, meaning it works for everything, that has very wide scope, gives good yield, little waste, high atom economy, little waste, is a click reaction. And here is an example. We take two bits and we've got our molecule. Click. That's all you need to know. Doesn't matter the mechanism, doesn't know how it works. For those of you who do know how it works, there's a paper on the next slide which tells you the mechanism. But the key to why this is so important is it's completely reliable. We have orthogonality in the two groups, which means that we can do chemistry quite easily. We can literally put anything with anything, and the yields are extraordinarily high. And just to give an impact of click in chemistry, that word, you can't now do this analysis on Web of Science because there's just too many papers. So the last time I did it was 2010. But you can see that this is where the Sharpless review appears in the literature, and this is how many papers that have click in the title, and it now has gone through the roof. And I actually did this yesterday, and it's now 9,222 papers with click in the title, cited by a further 220,000. That's impact in a discipline. And if you're interested in the mechanism of the click reaction, that's where that appears. Our second design block is our blue, our naphthalamides, and again, I won't bore you with the detail, but essentially these are extremely amenable to a range of synthesis. We can functionalize the top face very easily with amines. We can either do substitution chemistry here, or we can actually do some palladium coupling chemistry. Brilliant, brilliant molecules, extremely flexible to work with. And this was our first entry in the field. This was by Emiliano. Came in my office and said, want to make this, go for it. And it worked. And essentially what we have is our click linker, our fluorophore, which is off, our fluorophore, which is now on, and our metal binding unit. And here we have our fluorescence. And those of you who are more interested in fitting in KDs, the data are there. And this is now the sort of standard model for most papers in the field, where we look at the selectivity of our system over competing metals. So here are a range of metals which you can't read, but that doesn't matter. What I hope you can see, though, is that fluorescence doesn't switch on for anything else. If we throw in competing metals that you might find in a biological system, like sodium, magnesium, calcium, then we throw in zinc, and here we're throwing in 5 equivalents, so those that are in excess, we throw in 1 equivalent of zinc. We see recovery of fluorescence, and it's only where we get to metals that we expect not to work that we do see that quenching occurs, and we can't substitute out those metals. They work over a good range of pH, and when we put them into cells and we induce cell death, what we see in dead cells, which are in black, is more fluorescence than in living cells, and apoptosis is associated with increased zinc levels. This was a paper that took huge tenacity. It went to 5 journals. It was refereed by more people than I care to remember, and eventually we just gave up and went to inorganic chemistry, and has been cited 126 times to date. So, ChemCom. Oh, sorry, I forgot I was being recorded. So we then made some sensor materials. There was a serious side to this. So these are sol gel materials that we used a nanopipette. This was through some European funding, which was done by Kevin Flavin, who wasn't a postdoc with me, who was associated with the EU network. And there was a serious side to this because I was talking to a dental colleague at QM, Frida Fortune, who'd been there 6 months, and she said in the clinic in 6 months at QM, I've seen more cases of oral cancer than I've seen in my entire career, 25 years of practicing dentistry, more cases of oral cancer. And the only way that we can test this is to take, where there's a lesion in the mouth, take a sample. So literally carve a bit of it out and do some measurements. And in every case, zinc was present in elevated quantities. So the idea of this was we formed a sensor material that we might be able to detect zinc in a patient's mouth. The reason that there was so much oral cancer was because of the Bangladeshi community in the East End who chew cat, which is a leaf which gives a bit of a euphoric high. And we also did some electrospinning, which doesn't come out very well, but we made some very fine fibres, so we were trying to make high surface to volume ratios. I promised some people dancing earlier. So this is one of my ideas. It has actually been referred to by Matt Todd now in the literature as the ballerina complex. And so the idea was that perhaps if we could get our two fluorophores on a molecule and make them like this, and then when they bound zinc like that, we might be able to quantify zinc, because this would give us what's called a ratiometric sensor. This would give us an excimer, so we would have a different emission to this. Seemed like a really good idea. Did it work? No. But we had some fun, and we made some complexes, and the problem was that in solution, it didn't do that, it just did that, and then the zinc bound, and we got a twofold increase in fluorescence. We wanted to go a little bit further, though, so we're still doing a lot of stuff now, just in test tubes. We're not really looking at anything other than cells. So colleague Caroline Brennan at QM was an expert in zebrafish, or using zebrafish in her research. And Caroline very kindly offered to have a little look at our probes in some zebrafish embryos, which are a super biological model. And don't get me too squeamish about animal work, which I do get quite squeamish about, because I've owned zebra danios over the years. We have some currently, and they die. So I've lost fish. I could cope with this. And they do have high fecundity, so are easy to breed. And here are just a few of the images we got of some of our probes. This is the eye of a zebrafish embryo that's 5 days old. This is actually very different from the only two other papers in the field that use probes, because they saw zinc in the brain. And we didn't see that with our probes. So this seems to suggest a specific targeting the probes to different regions of biological space where there may be zinc. And in this one at the bottom, we can see the zebrafish gallbladder. That's actually its liver, and I think the spleen as well, from memory. Then the slide, advice to colleagues. Never go to a conference outside of the UK where no one knows about Channel 4 television programmes and try and explain a concept. But of course, today I can, because everyone knows about Kirsty and Phil and location, location, location. And so the extension of the work was to take our metal binding unit, our fluorophore, and to use a second click reaction now to extend our ability to now target our probes to specific biological space. Some chemistry for those of a certain disposition in the audience. For those who are not, this represents a year's work of one PhD student, actually more than a year's work. Jess Pancioli, who I mentioned at the start, we developed this chemistry in a stepwise manner. It all worked beautifully. We went from starting material, we did our click reaction with a model substrate on the top, good yield. Did our click reaction on the bottom face, good yield. Last one was a bit slower, but we got our 2 clicks on, perfect. We said, let's do it one pot, let's do it sustainably, let's reduce our impact, because we've got 1, 2, 3 columns here. Do it one pot, 1 column, 1 purification step. Didn't work. And it took us ages to work out. And what the reason was this click reaction here was being poisoned by the bromide generated in this step here, despite the fact you can do click reactions with copper bromide. And eventually we got around that. We found that by adding a little bit of ethanol to solvate the bromide, we could make the reaction work very well, and it went through in 85% yield. We made a whole bunch of targeted units. I'm going to focus exclusively on these ones. So what we have here are a long-chain alkyl group, basically a fatty group, which I've tried to symbolize here, which nestles into the outer cellular membrane, and our probe sits on the outside. And at the bottom, we have an islet of Langerhans from a mouse, where what we're doing is loading our probe first. It's actually this probe, loading our probe first, and then washing a solution of zinc over the islet. So it's not really a biological experiment. And then we have some other probes that you can see there that targeted different bits of the cell. And I just wanted to put this in because this is actually a really serious message from, I think, a social and health perspective. Type 2 diabetes is killing the planet. We're doing our best to kill it in other ways, but it's actually killing us. And these are some stats from an NHS England study, which are eye-watering. £6 billion per annum nationally. 1 in 6 patients in hospital have diabetes, of which 9 out of 10 have type 2 diabetes mellitus. It's predicted to rise to that, and the associated treatment costs $13.5 billion. Why zinc, though? This is the crystal structure of insulin, and at the centre of it, what you see is a little zinc atom. So when insulin is released from pancreatic beta cells, so is zinc. And what biomedical scientists who work on type 2 diabetes research do is use, or like to use, is zinc as a surrogate for insulin. And what we have now at the bottom is a slightly more advanced experiment to the one that we did in the previous slide, which is where they're now polarizing the cells, and we're seeing zinc being released with insulin, which is seeing increased fluorescence on the islets. Then we move on a step further to some really, really clever and advanced cell biology, which actually I really genuinely don't understand. I've read this paper about 6 times, and the only bit I understand is the chemistry. But it's an incredibly impressive study, of which this is only a very, very small part. But in effect, what we have are 2 molecules. One which has this diazo unit here, which can photo switch. So with light, it can flick from one form to the other, which Guy and David represented in this form. So this form is this one, and this form is this one. So when they shine a laser on a specific cell, they can open and shut this ATP-sensitive potassium channel. They then use our chemistry on the surface. And so they can now image calcium release, sorry, not calcium release, why would I say that? Zinc release, that's like swearing in the zinc community. Zinc release from individual cells. And what they found was that within the islet of Langerhans, there were 2 different sorts of cells, and they termed them they termed them hub or pacemaker cells and follower cells. And what they find is if they switch off the hub cells using the chemistry, the whole of the islet dies. It stops working altogether. Whereas if they switch off the follower cells, it keeps on working just fine. And so they hypothesized that because of the differences in the metabolics and genetics of the cells, this is the bit I don't understand. Jonathan, you can explain it to me one day in a one-to-one. They hypothesized that the type 2 diabetes is caused by the problems with these hub cells. I had intended to give some quite up-to-date research, and again, when Raphael reminded me yesterday that this was recorded, there was a very rapid re-editing of the talk. But this is where we're going at the moment. So this is an organelle-targeted probe. This is the probe with an organelle-targeted fluorophore or dye that biologists use to show, and this is the merged image, and basically the closer that is to 1, the better the co-localization. So what that's showing us is that we can co-localize into another organelle in the cell. And Li Fang is leading on this in London, and he's doing an absolutely first-rate job. I'm very grateful to him, and I'm pretty confident that we can now go after any organelle in the cell with a bit of work and a bit of chemistry. I just want to finish off with the final bit of the talk, which is talking about breast cancer and zinc. So we were actually talking about nails at the weekend, and I'd completely forgotten that biotin, vitamin H, is alleged to strengthen nails and hair. But it was also used by us to target breast cancer cells. So I was flicking through a table of contents alert a while ago. I used to spend Friday afternoons in the library going through hard copy of journals, and don't do that anymore. I think we should, because I think we'd have some good ideas. But I was flicking through this ChemCom, and I saw a paper that was targeting a platinum anti-cancer drug to a cell using biotin. I thought, oh, that's interesting, knowing what I did about some of my collaborators' work on breast cancer and zinc transportation. So we wondered if we could biotinylate one of our probes, whether this would be hoovered up by cancer cells, because cancer cells are metabolically turning over like fury. They need as many nutrients as they can get, and they have this, what's called the multivalent vitamin transporter channel that's overexpressed massively. So they have loads of these vitamin transporters so they can get as many nutrients into the cell. And of course, if you stick a vitamin onto a probe, maybe it'll work. So it did. In the interest of time, I won't bore you with some more supermolecular chemistry. We did some DFT calculations, which actually showed that the mechanism that we've been talking about for years and years and years in our probes of PET, from that high energy pair of electrons onto the fluorophore, is wrong. And it's actually, in this case, entirely to do with restricting molecular motion of the ligand on binding to zinc, which is interesting. But did they work? They did. They worked beautifully. On our left side here, we have breast cancer cells. So we have at the top, no probe. We have a 100 micromolar probe, where we're now starting to see zinc. These are just 2 different channels. We actually prefer the green because we don't get background fluorescence from the cells. So we see the cells filling up with fluorophore. If we then load the cells with more zinc, we see that the whole cell is full. and so that the zinc is the probe is right the way across the nucleus as well as the cytoplasm. And importantly, when we do the same experiment with skin cells, all we see is this very low-level background fluorescence. So it worked. So we have a tool that we can use, which is currently in a lab in Cardiff, and I'm hoping for an email that's telling me it's worked very soon. So that brings me to the end. Thank you all for coming. Thank you for listening. Thank you for occasionally laughing. Thank you to my new colleagues here. Thank you to my former colleagues at my previous institution, friends, teachers of chemistry and karate, but most of all, these three ladies here. Thank you very much.